Good evening. Welcome to the QCIS channel. Well, on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and what I'm going to get into tonight, and most likely further down the line, is we are going to do a lot of STEM, but I'm going to cover a lot of information, and it's going to help me out as well. That goes into the fundamentals of engineering examination. Now, when we deal with the fundamentals of engineering examination, that is the first step to licensure to become a professional engineer. Of course, if you're a surveyor, they have an exam called the FS examination. And that's the first step before you get your PS. If you are a geologist, same thing. And I'm going to tell you, these exams, they're not there to trick you. They're standardized examinations, but they are tricky. I know I have taken the fundamentals of engineering examination 3 times, and I've been unsuccessful myself. And I'm going to do these videos not only to teach others, but to teach myself. Now, some of the subjects I'm going to cover, a number of them are going to be in the environmental sector. I will cover mathematics. I will cover some statics. I will cover some fluid mechanics. I will cover some chemistry. But tonight, I'm going to cover something called stoichiometry. Now, stoichiometry is in chemistry. And in stoichiometry, what you do is you basically deal with a lot of chemical reactions. And the units you're going to use moles, you're going to use grams, you're going to use molecular weight. It's when we deal with chemistry and in some physics, one thing that individuals must understand, and I'm going to do a video on that as well, is unit conversions. A number of individuals on this FE exam, and including myself, we get the units wrong. Now, is it good to memorize some of the units? Like, I'll tell you what, 1 gallon of water. Right now, off the top of my head, I know that's right around 8.34 pounds. I know 7.48 gallons is a cubic foot. I know 1,728 cubic inches is a cubic foot. I know when we deal with moles, of course, when you get into your periodic table, you go from grams to moles. I mean, what I like about this, it's very interesting because it teaches you how to think, and there are also conceptual questions. Now, what I'm going to do is I'm going to share my screen. And in my screen, just bear with me. I don't want that shot. Let's try something different here. Here we go. That's what I want. And we're also going to, when the time comes, we're going to share a little bit of sound as well, because I'm going to get into a video. And this is all coming from Kim Talk, and I'll post this information at the bottom of my video. And when I actually get a real whiteboard, I don't know how to do whiteboard on Zoom yet, but when I learn it, I'm going to have some fun with it because I want to do problems. And one thing that individuals do, and I did it myself, I gave up on the fundamentals of engineering examination. I listened to people. Well, the bottom line is when you listen to people, particularly the ones who tell you they don't need it, that's because they don't have any anticipation of taking it. They're comfortable where they are. Let me tell you something. If you are going to be an accountant, a lawyer, even in social work, get your license. License means a lot. Now, as you see, we're in Chem Talk, solving stoichiometry problems. Now, does everybody know what H2O is? H2O is water, two hydrogens, one oxygen. Now, what is H2O2? H2O2 is hydrogen peroxide. Now, one of the aspects of solving stoichiometry problems is you have to learn how to balance equations. Now, there are a lot of core concepts like you see right here. And you must also understand equations of equilibrium. Now, when we deal with stoichiometry, which is part of chemistry, you must understand that when there's a fraction, there are always your product over your reaction. So basically, let me tell you what I mean. When we deal with a chemical problem like you have, this is a hydrogen peroxide problem. It's already balanced. The first part of this equation is what we call your reactant. The last part of the equation is what we call your product. So if you want to find out the answer, you take your product and divide it by your reactant. That's like taking, let's say you have an equation and looking at the equation, there's two right here. And although you don't see it, it's invisible. It's just like a card game. There's no number one in cards, but we already know that the ace is a one. Well, right here in front of your oxygen, there is no number for your coefficient. Well, that coefficient is really a one. And then the two right here, that is what we call your subscript. And subscript is very important because when I go and actually have to find the molecular weight, I'm going to take hydrogen, which the atomic mass, the atomic number of for hydrogen is one, but the atomic mass is 1.008. Now, if I want to find out the actual weight of H2, I'm going to take the subscript 2 and multiply it by 1.008 and get 2.016 grams per mole. And when it comes to stoichiometry, which is part of chemistry, you have to know how to balance equations. Now, again, what is stoichiometry? Well, stoichiometry is math having to deal, or it's having to do with chemical reactions. Now, there are different types of calculations you can perform. So basically, when we deal with stoichiometry, the most common unit, you have Avogadro's number, which is 6.022 times 10 to the, or 6.023. It's in that range times 10 to the negative 23 moles. I could be wrong. Somebody could correct me on that, but right off the dome, it is close to what Avogadro's number is. And that's also going to be used when it comes to conversion factors. Well, basically, stoichiometry deals with moles because moles are the most common, but you can do masses, you can even do percentages. Now, what we have when it comes to stoichiometry, we have a ratio. And the ratio comes into play when we talk about relationships of elements or molecules of specific problems. So there is an exact ratio between the coefficients and the reactants and products needed for a reaction to proceed normally. So, like I said before, when we deal with problems, okay, this problem is already balanced. Now, stoichiometry problems, and one that is very, very common, we have carbon hydroxide. Well, we deal with balancing equations. Now, here's what we do. The main idea when we balance equations, we want to get the same elements on each side of the equation. And if you do that, it makes it much easier to do your calculations. Now, like I said, here we have C2H2O2, which yields, this arrow means yields, CO2H2O. Now, as I'm looking at that right now, is that equation balanced? I can tell you right now that equation is not balanced. Why? Because when I look on my left side, I have two carbons. When I look on my right side, I have one carbon. Now, when I look on my left side as well, I have two oxygens. But when I look on my right side, I have three oxygens. So what am I going to do to balance this equation? Well, I'm looking at what I have here. All right, because I have a carbon here and a carbon here, I need to balance this equation. So again, I can have the same elements on each side. So the first coefficient I'm going to find is 2. Why? Because I'm going to need to make this H2. Well, it's actually going to be 2 times 2. It's going to give me 4. And this is going to be 4. Why? Because, okay, we're going to have 4 carbons here. So we're going to have 4 carbons here. Now, when you deal with multiplying coefficients, and you have to be very, very careful. Like here, this is a 1. So if I actually put, let's say I have 5 here, I'm going to put a 5 right here, and I'm actually 5 times 2. It's going to give me 10 molecules of oxygen. And basically, this is what you have to do. After you balance the equation, then what you're going to do, this is when you're going to set it up. And remember what I told you about moles. So what I'm doing is I'm going from, I believe this is, I believe C6H6O6. It might be benzene. Might be benzene. So what I have to do, I have to go from benzene to carbon dioxide. Now, when you deal with stoichiometry problems, you have to look at what's given. Now, generally, you always have what's given and what's needed. So, like in this problem right here, we need to figure out how many moles of carbon dioxide are made from 2.5 moles of glucose. That's what it is. Correction. Glucose. You know what glucose is? Glucose is sugar. I said benzene. It's no, it's not benzene. C6H12O6 It's glucose, just like NaCl. You know what that is? NaCl is sodium chloride. What is sodium chloride? It's salt. So what I'm going to do is show you how to do this. This is an example. So by looking at the coefficients, 1 mole of glucose, 2 moles of CO2. So what I'm going to do is start. What do we have? You're always going to put what you have first. And then you're going to go into what we call the proportion. And once you get into the proportion, that's when you can go from one chemical to another. Like we start out in glucose. Now, if I went and found the atomic number, I believe you have six oxygens, and right around 15.99916. So if we really wanted to multiply this out, our weight, we'd have 96 oxygens, plus we'd have 12, that'd be 108. And I believe carbon, I don't know if it's 32 or not. 6 times 32 would be 100. 6 times 32, that would be right around 192. That's so right around there. So we would basically have almost 300 grams of C6, and I'm just estimating it right now. But what you would do in order to go from one element to another, you're going to convert. And what you need to know when we deal with stoichiometry is you can go from moles to moles, you can go from moles to liters, you can go from grams to grams. And when you go from grams to grams, this is when you're going to use the periodic table. But you have to look at what you have. Now, how can you determine your moles? Very, 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 very easily. You have to look at your coefficient. Now, right here, they're already giving you 2.5 moles, but how did I get 2 moles of CO2? Go back to your equation. Your coefficient is your mole. Now, how did I get 1 mole of C6H6O6? Very easy. That was already given. So basically, you're still staying in moles. This is a mole to mole equation. Once you multiply everything, you get 5 moles of CO2. Now, the same thing, when I tell you about grams, we're dealing with mass now. So the equation is already balanced. So how many grams of glucose was initially used if 10 grams of C2H5OH were produced? Okay, now, again, basically, when you read the problem, when you're asked a question, that's what you need. Because what you're given, you're going to have to take what you're given to find out what you need. Now, basically, when it comes to the moles, you're always going to look at the coefficients of your problems, your reactants and your product. Now, when it comes to your mass, now we're in SI units. So SI units, we're going to, which is metric, we're going to use grams. So what you have to do is go to your periodic table and you have to find out what this element is. And you're going to do some mathematics. So you're going to take the 10 grams that you're already given. You want to, now we're going to moles again. So how many moles of C2H5OH are they? Well, we start off with 10. So The conversion factor is we're going to take 1 mole, we're going to convert it. We already found the weight via the periodic table. Now, where do we go after this? Very simple. We're going back to your equation. This is where you find your ratio. So 1 mole of C6H12O6. How do they get 1 mole? Your coefficient is 1. And 2 is for C2H5OH. Your coefficient is 2. So now, one good thing about stoichiometry, you know you're on the right track if your units cancel. So the moles, they cancel. The C2H50H, they cancel. So you have 1 mole. So guess what we're going to do? Now that we have what we need, we're going to actually go to your gram table. So, or your periodic table to find out your weight of glucose, which it's already been done for you, 180.156 grams. So what we're going to do, we're going to take that and we're going to divide it by 1 mole. Why? Because we already have 1 mole for your coefficient, which is part of your ratio. We want them to cancel. And like I said, when everything cancels, you get 19.55 grams of glucose. Again, here's another problem. You deal with moles here. Now, let me tell you something. When we deal with something that's aqueous, that means it's a water substance. When we deal with an S, that means it's a solid. So what we have here, you burn an unknown amount of hexane. Hexane, which when you hear the word hex, that should already trigger, that's going to be 6. So hexane is C6H14. Now, again, hexane has a mass, and you get your mass from your periodic table. Your periodic table is going to give you grams per mole. Grams per mole. And the equation is already balanced right here. Now, what I'm going to do, I'm going to go in, I'm going to introduce you to some stoichiometry. Fair use. I'm going to look at a couple of videos so you can actually see how everything is done. And they're going to explain it just like I explained it. So fair use. These videos are for educational use only, and this is for Chem Talk. Fair use.
Hey everyone, and welcome to Chem Talk. In this video, we will be going over how to do unit conversions using stoichiometry. We will also be focusing on using the mole and how to use molar mass in calculations. Stoichiometry is the use of math in chemistry. Using stoichiometry, we're able to convert between many different units, including moles, atoms, grams, and liters. In order to do these conversions, all we have to do is set up the equation and make sure our units cancel out correctly. An example of this from life is using coins. In this example, we have 25 pennies, but we don't know what it converts to in terms of quarters. But we do know the conversion to nickels, so we'll start with that. Say for every 5 pennies, we have 1 nickel. We make sure the units are canceling on both sides of the line, pennies on the top left, and now pennies on the bottom. So now we know for every 5 nickels, we have 1 quarter. We add in this conversion rate, putting the nickels on the bottom to cancel out with the nickels that we had on the top. We are now able to cancel out the units that we do have, pennies for pennies and nickel for nickel, leaving us with the unit that we wanted, the quarter. We now multiply the numbers on the top row, 25 times 1 and 1, which gets 25, and 5 times 5 on the bottom, and this 25 over 25. 25 divided by 25 is 1, which leaves us with 1 quarter. As we know, 25 pennies is equal to 1 quarter. This is the general idea of stoichiometry in chemistry. We exchange units using conversion rates until we reach our desired answer. In order to use stoichiometry effectively, we need to learn the most important and common conversion tools. In chemistry, we often refer to amounts of things in moles or moles, spelled with or without an E. This is because samples in chemistry contain a large amount.
I'm going to stop right there. That number that I mentioned to you, this is called Avogadro's number. 6.022 times 10 to the 23rd. I actually said negative 23rd. I stand corrected. It's 20, it's to the 23rd, 10 to the 23rd power, which is a large number. Let's continue.
Of atoms or molecules in every sample. Additionally, this allows for ease of conversions between units. For convenience, we use the unit of a mole. A singular mole is 6.022 times 10 to the 23rd particles. We often refer to things as a mole of atoms, a mole of elements, or a mole of a molecule. When we say there are 1 mole of chlorine, it means there are 6.022 times 10 to the 23rd atoms of chlorine. Similarly, when there are 2 moles of nitrogen, there are 12.04 times 10 to the 23rd nitrogen atoms. As an example of this, we have the question, how many fluorine atoms are in 3 moles of fluorine? We start off with the 3 moles of fluorine, and from the previous slide, we know there's a conversion rate of 1 mole of any element to 6.022 times 10 to the 23rd atoms. If we do the same stoichiometry setup, canceling out the units, multiplying and dividing across, we'll get 1.81 times 10 to the 24th atoms of fluorine. Another stoichiometric tool we have is molar mass. On the periodic table, usually below the symbol for each element, is the molar mass. The molar mass refers to the mass of 1 mole of that element. The picture to the right shows a zoomed-in picture of the carbon on the periodic table. The number below the C is the molar mass of carbon, around 12 grams per mole of carbon.
Again, just as I explained it to you before, carbon. Here's the periodic table. Now, years back when I was in middle school and high school, the periodic table only had 103 elements. Now they're up to 118. Now, you see this number right here. Here's the element of carbon. Here's your number of carbon. I believe that's your atomic number. You have your, and let me give you a little bit about the periodic table so you'll know exactly what I'm talking about. Because in the periodic table, you have metals, you have gases, alkalis. You have a lot of elements, and that's what these different colors are for in a periodic table. Leave all of your gases. You have your iron, your nickel. There's a reason why they have different colors. Some are gases, some are metals. But let me break it down. This number right here, this 6, that's called an atomic number. This C right here is carbon. That's your element. Now, this number right here, this number is 12.011. That's what we call your atomic mass. and your atomic mass is in grams per mole. That's exactly what he's talking about. Fair use. Let's continue.
This exists for every element on the periodic table. For example, 1 mole of hydrogen weighs roughly 1 gram. When looking at zinc, the atomic mass is 65.4 grams per mole. For every mole of zinc, there are about 65.4 grams of zinc atoms. We can use the molar mass to convert between grams and moles. Furthermore, we can use moles to convert between particles such as atoms, molecules, or ions. This is a common question that we'll come across when dealing with molar mass. How many grams are in this amount of moles? In the first example, we're given 2 moles of oxygen. From the periodic table, we know that 1 mole of oxygen is equal to about 16 grams of oxygen atoms. We correctly line up the units for our conversions, multiply across and divide, and we find that 2 moles of oxygen is about equal to 32 grams of oxygen atoms. We can do a similar problem with an entire molecule, as long as we know the molar mass of its parts. We can add them together and get the molar mass of the entire molecule. So for water, or H2O, it has 2 hydrogen atoms and 1 oxygen atom. Hydrogen has a molar mass of 1, and oxygen has a molar mass of 16. Adding the 16 plus 2, 1 for each hydrogen atom, equals 18 grams per mole of water. Using the same stoichiometric conversion, we can find that 5 moles of water equals 90 grams of H2O. In this final example, we combine both the use of moles and molar mass together. The problem states, how many atoms is in 12 grams of lithium? So let's remember the different tools we have. We have the molar mass of lithium, which is 6.941 grams per mole, which we get from the periodic table. Additionally, we know the amount of atoms in a single mole, which is 6.022 times 10 to the 23rd. We keep the same process as previous problems. We line up our conversion rates, making sure our units cancel out. In this case, we must flip the molar mass ratio in order to line up the grams of lithium on the bottom with the grams of lithium that we started with. We do the same thing with the moles of lithium and the atoms of lithium. We cross out our units, then we multiply, cross, and divide. Our final answer is 1.04 times 10 to the 24th atoms in every 12 grams of lithium. Stoichiometry is the heart of chemistry. In a chemistry laboratory, different formulas or reactions require certain measurements or dilutions that aren't always obvious. Stoichiometry is a skill that is practiced and used in every single chemistry reaction in every chemistry lab. It is an important skill to learn to become proficient in chemistry. In this video, we learned that stoichiometry allows chemists to convert between units and determine accurate measurements. We also learned that a mole is 6.022 times 10 to the 23rd particles, but it also allows us to do fluid conversions between units and measurements, such as atoms, molecules, ions, or grams. Additionally, we learned that the molar mass is available on the periodic table, and it is grams per mole, and it allows us to convert between grams and moles fluidly for every element. Finally, we learned that we must cross off units to achieve our desired unit result. And that's it for today. Have a nice day, and remember to talk chemistry.
Again, when you deal with chemical problems, especially when they ask for grams, you got to look at what they're asking. If they're asking you for atoms, then you know to use Avogadro's number. 6.022 times 10 to the 23rd atoms equals 1 mole. When they ask you for grams per mole, then you know you're converting something either from grams to moles or moles to grams. You're going to be looking up your molecular weight from the periodic table. Now, again, you're going to have compounds like benzene, salt, you're going to have hydrogen peroxide. So you need to know when we deal with the subscripts, as I explained to you before, the equations to balance them out, you're going to have coefficients. Well, you already have a coefficient of 1 in front of all of your elements. You have your reactants and your products. Now, your subscripts indicate how many atoms you have. And a good chemist is going to understand conversion factors. And conversions aren't just in chemistry. They're in engineering, period. They're even in cooking. How many teaspoons make a tablespoon? How many teaspoons make a cup? And if you're going to understand conversion factors, chemistry is the best place to start. Now, let me see if I have another one for you. Let me share my screen once more. And we're gonna deal with some more here. We're actually going to show you how the problems are done. Again, this is from Chem Talk. Like, share, and subscribe to their channel. This is for education and for everybody who's taking the FE exam. This is the best place to relearn chemistry. I'm going to teach myself, and I'm going to teach it to you as well. Fair use. Let's go.
Hello, and welcome to Chem Talk. Today, we'll be learning about stoichiometric conversions within balanced equations and how to calculate amounts of reactants and products in a chemical reaction. So, let's talk about it. First, let's go over some key terms and concepts. We'll be utilizing some basic unit conversions between things such as atoms, moles, and grams. And we'll be using conversion factors such as molar mass and Avogadro's number. If any of these terms look new to you, check out our video called Basic Conversions, Molar Mass, Moles, and Atoms. And then come on back here. A key concept in reaction stoichiometry is the idea of a mole ratio, which, for two compounds, is the stoichiometric relationship of their quantities. To identify the mole ratio of two separate atoms or molecules, take a look at their relationship. For instance, in this molecule of methane, or CH4, there are 4 carbon atoms and 1 hydrogen atom. We have a total of 1 molecule of methane. So, the ratio of carbon to methane here is 1 to 1. For every methane atom, there is 1 carbon atom, and vice versa. The ratio of hydrogen to methane is 4 to 1. For every methane atom, there are 4 hydrogen atoms here. And, similarly, the ratio of carbon to hydrogen is 1 to 4.
Now, just a point to let you know what has happened. You also have to know your elements too. Like here, you're going to get into, especially if you get into materials engineering, you're going to deal with all kinds of shapes, and you're already starting. This would be like a quad here, because you have, again, 4 hydrogens. This is where you get. This is how you find out about your elements. 1 carbon, and you have 4 hydrogen. That makes up your methane. That's known as CH4. Let's continue.
If we up the scale, we can use these ratios of atoms to think in ratios of moles too. If we convert both of these atoms to moles, we can see that Avogadro's number cancels, and we're left with the fact that the ratio of two atoms of something is the same as the ratio of two moles of something. Okay, so now we know a little more about mole ratios. Let's take a look into how we can apply this stoichiometrically with a quick example problem. So the question here is how many moles of oxygen are there in 3 moles of silicon dioxide, or SiO2? The first step for us is to identify the mole ratio. In every 1 mole of silicon dioxide, there are 2 moles of hydrogen. For every silicon dioxide molecule, there are 2 oxygens and 1 silicon atom. We can then establish that the ratio of oxygen to silicon dioxide is 2 to 1. So, we have our conversion factor now, and we can multiply. We have 3 moles of silicon dioxide, and know that there are 2 moles of oxygen per mole of silicon dioxide. So, our final answer will be 2 times 3, or 6 moles of oxygen total. Okay, we've learned how to do this with individual molecules. Now, let's apply it within reactions using stoichiometric coefficients. Stoichiometric coefficients are the numbers in front of each reactant or product in a chemical reaction. So, let's say we have this reaction here, the combustion reaction of propane. Once we balance this reaction, like so, we can use these coefficients to establish mole ratios. Here, the ratio of propane to O2 gas to CO2 gas to water is 1 to 5 to 3 to 4. We can use these numbers to establish mole ratios. For instance, the ratio of moles of propane to moles of carbon dioxide here is 1 to 3, or the ratio of moles of O2 to moles of water is 5 to 4. Now, let's see how to apply these mole ratios within an example problem. How many moles of aluminum solid does 4.8 moles of Al2O3, or aluminum oxide, produce? So, our first step always is to balance the reaction. We're given this unbalanced reaction, which is the decomposition reaction of aluminum oxide. So, we can go ahead and balance it like this. Once we've done that, the next step is to establish the mole ratio that we need. Our question is asking us to convert aluminum oxide to aluminum solid. So we'll put aluminum at the top of our fraction and aluminum oxide on the bottom. Looking at our balanced reaction, we can see that the stoichiometric coefficient in front of solid aluminum is a 4, and the coefficient in front of aluminum oxide is a 2. We don't have to, but we can simplify this fraction, this ratio, down to 2 over 1. For every mole of aluminum oxide we use, there will be 2 moles of aluminum solid produced. Our last step is going to be to calculate. We start with 4.8 moles of aluminum oxide, as the question says, and multiply it by our new ratio, 2 moles of aluminum per mole of aluminum oxide. Moles of aluminum oxide will cancel, and we're left with 9.6 moles of aluminum solid, which is our answer. Now let's do another more complex example. Our question here is how many grams of aluminum oxide does it take to produce 20.8 grams of O2 gas? We're also given the molar mass of aluminum oxide and the molar mass of oxygen gas. So let's write out a quick plan. In the previous examples, we've gone from moles of reactant to moles of product, but here we'll go the other way. We're given an amount of oxygen and need to convert that to amount of aluminum oxide, which is a reactant. So our arrow will go this way. However, this time, unlike the other examples, we have the extra step of converting grams of O2 to moles of it, because the question gives us O2 in grams, and, at the end, moles of aluminum oxide to grams of it, because that's what our question asks for.
And when you're doing these problems, make sure you read the problem correctly and start to work slowly, because when they get complex like this, you also have to look at, now there's no equation up here, but you have to make sure that your equations are balanced. And that's the first thing you need to do. And you need to find out what your coefficients are so you can create your, I call it your coefficient ratio, because even though you have moles on moles, you're going to have two different moles. You're going to have moles, but the elements are going to be different. And again, what you're trying to do to get to the last step, you're trying to get what you need based off of what you're given to get the end result. Basically, when we deal with chemistry or physics or any other science, we're dealing with a solution. Fair use. Let's continue.
We'll think about this plan in the last step, but it's important to have a good plan going into the question. The first thing we'll do again is balance the reaction, but we finished that in the last question. 2 moles of aluminum oxide decomposes into 4 moles of aluminum and 3 moles of O2 gas. The next step, again, will be to establish our mole ratio. We're converting O2 to aluminum oxide. The stoichiometric coefficient of aluminum oxide is 2, and the stoichiometric coefficient of oxygen is 3. So, our mole ratio will be 2 to 3. Now, for the final step, calculating. We've established that our mole ratio is 2 to 3. Our first step here, according to our plan, is to go from grams of O2 to moles of O2, which we can do using the given molar mass of O2. The next step, moles of O2 to moles of aluminum oxide, can be done using the mole ratio we established. Finally, we can convert moles of aluminum oxide to grams of aluminum oxide using its molar mass, which were also given in the question. Now, we can write out our work. We start with 20.8 grams of O2 and multiply that by the molar mass of O2 gas. Our units cancel and we're left with moles of O2. Next, we can convert those moles of O2 to moles of aluminum oxide using our mole ratio that we established. Now, we have moles of aluminum oxide, and as our last step, we convert that to grams using its molar mass. Now, we can write out our work. We start with 20.8 grams of O2, multiply that by the molar mass of O2 gas. Our units cancel, and we're left with moles of O2, which we can convert to moles of aluminum oxide using our mole ratio. Now, we have moles of aluminum oxide, and as our last step, we convert that to grams using its molar mass. Those units cancel, and we're left with 44.2 grams of aluminum oxide needed to produce 20.8 grams of O2. In summary, we've learned that the mole ratio of two compounds is a stoichiometric relationship between their quantities. We also learned that the stoichiometric coefficients of a balanced reaction are the numbers in front of each compound in the reaction. Finally, we learned how to use stoichiometric coefficients to establish a mole ratio between two compounds, which we can then use to calculate the number of grams or moles in a compound. Be sure to check out our website, chemistrytalk.org, for more great chemistry, biochemistry, and organic chemistry tutorials and content.
That was excellent content. That was just a summary of what I talked about, and you got a chance to see how the equations were constructed. Now, the equations can get even more and more complex, but just like every science, if you don't understand the basics, you're never going to understand the complexities, because chemistry gets into pH. So you're going to have your Cl, your oxidation. And when we do oxidation, that's where you see that plus, like hydrogen. Hydrogen plus is it's oxidation. Reduction is where you see the minus, and this is where you're going to come up with your, when we get into the pH, you're going to get into your negative 23rd, your positive 14. But if you're going to take the FE exam, particularly if you're going to take chemical engineering, other disciplines, and environmental engineering, you're going to see a lot of this. And I'm going to go over different aspects of the FE exam. Like I said, I'm not only teaching you, I'm teaching myself. And in order to be a good engineer, you should understand the concepts. And the basic concept is not only the math, you need to understand conceptual questions too. They may ask you, well, why are you having a 2% drainage from a road? Well, you say, well, slows down the velocity, something like that. Uh, the FE exam consists of conceptual, and it also consists of calculating and getting solutions and utilize your calculator. But the good thing, if you have your resources for the FE, like me, I'm doing the environmental, and this is one of the books I have right here for the environmental. Um, some of the information is outdated, but the problems never change. So, the bottom line is what you need to understand when it comes to the FE, you need to understand what the NCEES requirements are. Look at the specifications. Look how many math problems you're going to need to know. Now, stoichiometry, again, if you're going to be taking other disciplines, environmental and chemical, that's an area that you need to know. It's about 7 to 11 problems on that FE examination. Now, a word to the wise is sufficient. The FE examination is timed. But while you're practicing, the best way to do it, there's a lot of resources out there, but you have to look at your learning style. And as I'm helping you all, it's also helping me teach it so I can learn it better, so I can sit down and be confident about this FE exam. Now, some people that you can watch, Jeannie Prep, very good. The courses are lifetime courses. She breaks it down really well. Farouk on Direct Hub, he breaks it down. You can look at some of his material. You also have Civil Engineering Academy. Now there are some expensive ones out there like PPI to Pass, very expensive. They have materials. You can get them from Amazon. I have a lot of the environmental, and also, so you'll know this. When you take the environmental, or you take chemical, or you take civil, take what you know. Now, I'm going to feature some individuals who are going to explain this information a lot better than I can explain it. But I have common sense, and I'm going to feature individuals who've already passed it, and it's going to help all of us out because engineering is a good field. And if you want to advance in your career, you have to know the subjects. Even after you take the test, you should still know something about the subjects because it's going to help you. And a lot of us, yes, we don't use calculus, but when you have to use it, I guarantee you'll pick up a book and relearn it again. Learning is fundamental. You learn through 4 years of school. You go back to the basics. You start off with the basics. You get to the complex equations, but everything starts from the basics, and that's what you learned off of tonight's course about stoichiometry. And I'm gonna get more into stoichiometry because I haven't featured the oxidation equations. I haven't featured the actual reaction equations where you combine oxidation and reduction equations with stoichiometry equations. There's carcinogen equations, all kinds of equations. But the bottom line, it's all about learning. And once you have grasp of the concepts, you'll be comfortable. Now, on the FE exam, don't expect to get everything right. I'm just going to tell you what it is. Get out of the way what you know. And the bottom line is look at the specs from NCES, but also learn the material because you're going to have to use the same material when you take the PE examination. Yeah, you know, you get books like this. A lot of people say, oh, it's just for the FE exam. Actually, use them for the PE. You know, one thing about engineering, about anything else, repetition is the mother of all teaching. It's a skill. When you can repeat it over and over and over and over again and become confident with it, it's not a fluke. But if you do it one time, it could be luck, like a Hail Mary in football. It's luck. When you can repeat something, it's not luck. That means it's working. So again, when it comes to learning this stoichiometry, organic chemistry, physics, sit down and practice problems. Understand what goes into the conversion factors. Because in every aspect of engineering, you're going to have to convert. Some of them, they're going to be right there for you, like 12 inches equal a foot. Everything is going to be out there. You're going to have to convert from SI units to English units. But again, that's all I have for you tonight here on stoichiometry. If you like what I just presented, please like, share, and subscribe to this video. And if you're looking for more of the social content, check out the 401 Talk Zone radio show channel. And once I record videos on the 401 Talk Zone radio show channel and the QCIS channel, post those videos up on my Twitter page. Now, since this channel, the QCIS channel, is an educational channel, the content from this channel also goes on to my LinkedIn page. And once again, thank you for viewing this content on stoichiometry from the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. And until next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.